Okay, this is my first attempt at doing an online group discussion, or my best effort to guide you through these problems in an effective manner for your learning. It's going to be imperative that you work on these problems as much on your own as you can, not just looking ahead to see what answers I give. Otherwise, I'm going to do the work for you, and when it comes to assessment and actually learning the material, you will have damaged your ability to learn. So do your very best to try and solve these problems as much as you can before looking further in this video. So you can approach it in two different ways. For today's reading, 23, 5 through 7, we're going to be going over concept questions 11, 12, and 13, and then exercises 22, 26, and 53. Okay, so you can stop the video now and go try and solve all those problems. Or you can go one by one. That's how I'm going to step through the video. Okay, so to start, let's consider concept question 11. I've drawn it here, but I want you to go refer to your textbook and look over that problem in detail, to read that problem and try to solve it. Think about what the main concept is. So you should pause the video now to go look at that problem. Okay, so if you've tried that problem and you're still a little stuck, think about what the main concept that is applied here. We're trying to rank the magnitudes of the electric fields at these points, and so we have to know what is the electric field inside a capacitor. So you can ask yourself that question, and if you go back to your notes, you find that the electric field is constant. Okay, the electric field inside a capacitor is constant. Everywhere inside a capacitor, the electric field is constant. And I'll point out that the electric field outside a capacitor is 0. If you have further questions about that, feel free to email me and set up an appointment so we can talk about that. But the important point here is that the electric field inside a capacitor is constant and just simply equal to the charge surface density, so charge per unit area, which is the Greek letter eta, over the constant epsilon 0. So it has no position dependence. Okay, and I like to just write that as Q over A over epsilon 0. Okay, so here we see that it is constant. This does not depend on position at all within the capacitor. So the answer would be that all the electric fields 1 through 5 are all equal. Okay, so let's move on to now concept question 12. Okay, so concept question 12, I want you to go and read that out of the text and then try to solve it to the best of your ability, and then come back. So go ahead and pause the video now and go look at that and try and solve that problem. Okay, so assuming that you've tried to solve that problem, you may have some questions. Again, thinking about what is the main idea. So 12 is, 12 says, well, you've got these two capacitors, one capacitor, or you got this capacitor in an initial state and a final state. Okay, they're made up of square plates with side length L, and the plates are separated by a gap D. Right, and the plates are given charge plus or minus Q. So what is the ratio E final to E initial if the initial and final electric, oh my goodness, sorry. You're going to have to bear with me. This is my first time trying to do this and feels really broken up. But so let me just jump to the question. What happens if you double the charge on the capacitor? How does the electric field change if you double the charge? And then part B, what if you double the side length of the plates? And then C, what if you double the gap? Okay, so the main idea here is, again, thinking about the main idea is, well, what's the electric field inside a capacitor? So this is pretty much going back to this first problem. We're like, oh, well, the capacitor is directly dependent or linearly dependent on the charge, the size of the charge, on the cross-sectional area A, inverse with A, and then this constant. So my question, or a question you should ask yourself, well, what does Q stand for? Does Q stand for the positive plate, the negative plate, the sum of the plates? What does it stand for? And I encourage you to go look back at the derivation for this. This was derived for two separate plates. Okay, a capacitor is simply the superposition of the electric fields from two plates, assuming that one is negative, the other is positive, and they have equal magnitude of charge, and they also have equal areas. So with that being the case, Q is then the amount of what charge? A is the area of what plate? You should pause the video if you want to pause before you hear the answer. Okay, the answer, hopefully you're able to get, is that Q is the charge on either plate, the magnitude. So if let's say plus or minus 10 nanocoulombs, well, this would be 10 nanocoulombs, and these have this same area A, and so we plug in that area A. So in this case, it's L by L. So our E capacitor is going to be just the Q, whatever the Q is. They just say plus or minus Q, so we don't add up. It's not 2Q. It's not 0. It's just Q, whatever the charge on one plate, magnitude, divided by the area, which in this case is length squared. Okay, and then that constant that just goes along. All right. So we've now recognized what the Q and the L mean. So with that, hopefully this problem is fairly straightforward. That if we now double Q, well, we're going to see that the capacitance must, or the electric field must double because it's directly proportional to Q. Or in the second state, if the length doubles, what happens to the electric field? Okay, so the electric field should go down by 4 times because it's inversely related to the length squared. So if the length doubles, then the quantity in this denominator here, it goes up by 4, and since it's the denominator, that makes it to be 1/4. So I'm going to write that out. If L goes to 2L, then E capacitor equals 1/4 E capacitor initial. So the final equals 1/4 E capacitor initial. Okay, now the third question is, well, what if you double the gap distance, the distance between the plates? What happens to the electric field of the capacitor? Okay, well, the question, where's D in here? The cool thing about capacitors, it has no position dependence. It doesn't matter how far these plates are apart. Okay, and so these there's no D here, so the capacitor or the electric field of the capacitor doesn't change if I change D. Okay, well that's finished problem concept question 12. Now let's move on to concept question 13. Okay, so go take a look at concept question 13 and try and solve that problem and then come back to the video. So pause the video now. Okay, so for some guidance on concept question 13, okay, we have this capacitor, and we are releasing a particle right in the middle of that capacitor. All right. Now the question is, if it's a positive object, we release a positive charge from rest in the middle of that capacitor. Well, where's it going to go? So it's the same capacitor as in 11. So I draw it here, plus, minus, and I release this particle here. If that particle is positive, what direction is it going to go? So the direction should be to the right, because it's repelled by the positive plates here, and it's attracted by the negative plates here. So it's going to move that way. If that charge is negative, so this would be if it was positive, if that charge is negative, then logic would say that it moves to the left, because it's now attracted to the positive and repelled by the negative. So it would move this way if it was negative. Okay. Now here's a question. What about a neutral but polarizable object? What direction will it go? Okay, this one's a little more tricky because the net charge is 0, so there's no net force, and if I stretch it, let's say it's going to stretch like this. Okay, because the positives repelled by this one, attracted by this one, the negative is repelled by this one, attracted by this one. But they've stretched the same amount, so if I truly release it at rest here, well, this one, the attractive force from here to here is the same as the attractive force from here to here, and you can say the same about the repulsive forces. And so there is no net force on this, which means it's not going to go anywhere. Okay, but the interesting thing is that this object will align with the proper field that it's in. So it wants to align with the proper field. And something that will be helpful later is dipoles, that's a dipole, want to align with the electric field they're in. So this positive will align with the direction of the electric field, and the negative aligns opposite it. And so they orient themselves. So if this was at some angle already as a dipole, it would flatten out or align itself with the electric field. So that's a useful thing to understand. But what I hope you recognize is everything we've done so far is simply using our basic understanding of like charges repel and opposite charges attract. So that's what we've done to analyze these things. Okay, so that's done with the concept questions. Now we can consider the exercises. Okay, so exercise 22. So go ahead and take a look at exercise 22, and then pause the video, and then come back after you pause the video and try to solve that problem. Okay, so this one is getting into the nitty-gritty of a capacitor. Alright, and so we have a capacitor that has a gap of 0.5 millimeters, and you've taken 3 × 10⁹ electrons from one disk and thrown them on the other disk, okay, which makes one negative and one positively charged. And then you have, we're given that the electric field strength is 2 × 10⁵ newtons per coulomb. And we're asking what is the diameter on a disk. Okay, so where do we start? Well, let's go ahead and list some knowns here. Okay, we've got a good picture of what a capacitor looks like. It's got plates, areas, and charge. So we're going to say that the gap between them is 0.5 millimeters, 0.5, or sorry, you can write it in meters, 0.0005 meters. Okay, and there are, we don't quite know Q, except that it is N times E. Now this little e is the charge of an electron, which you can find in the front cover of your book, and N is the number they give us. Okay, that's the 3 × 10⁹. Alright? And then we're told that we know the electric field inside, E capacitor, is equal to 2 × 10⁵. Okay, newtons per coulomb. Alright, so we know the charge by knowing how many electrons were moved. We know the electric field. We know the gap. We want to find, what are we looking for? We're trying to find the diameter of these disks. So we want to find D. Alright? Alright, which basically means we need to find the area of the disks. And then we note that they're circular disks, and so from the area we can use geometry to find D. Okay, if that's helpful, go ahead and pause the video now and go see if you can finish solving this. See where can you go from here. Okay, as a next little hint, if you still need a little bit of hint, we can go back up to this right here, or better yet up to this one. We can say that the electric field of the capacitor is equal to the total charge over the area divided by this constant. And we are truly just trying to find that area and then be able to find the diameter. Okay, so go ahead and now solve this for the area. You can find the value of this constant, 8.85 times 10 to the -12. That's in the front of the book. And again, the size of the electric field, or charge of an electron given by the variable lowercase e, that's 1.6 times 10 to the -19 coulombs. You can find that in the front of the book. Okay, go ahead and solve for this area. And then once you do, all you have to do is say A equals pi d squared over 4 and solve for d. And just as a hint, the diameter ends up being 1.9 centimeters. Okay. And it's good to try and assess this. Does that seem reasonable for a capacitor? Now, capacitors could be kind of any size. We've seen in some problems there are capacitors having 10 centimeter discs. Now, there's one thing in assessing this number that is important, is this equation does assume something. If you remember from a way back for a plate, that the electric field of a plate was also constant. That's where we got this constant field, was adding the two plates together. But it assumed you're really close to it compared to the edges, or how close you were to the edges. Or in other words, the area needs to be large compared to how far away you are. And so if we're using this, we're assuming that the electric field inside this capacitor, or the space inside the capacitor, is small compared to the area. This doesn't seem like a very big diameter, which means not a very big area, except that the gap is only 0.5 millimeter, which that's pretty small compared to this 2 centimeters. And so that means that this is a decent sized value. So remember, what's really important is recognize this is a very powerful equation, but it has a limitation. It's an assumption that goes into here. Okay, now let's move on to number 26. Okay, so go and look at problem 26 and see how well we can do this one. Alright, so at the back, this one, I hope you recognize, has a few different parts to it. We're going to have to use E capacitor equals Q over A over epsilon 0. Okay. And that's for part A. That's going to be very similar to what we've done already. We know the size of the charge. Okay, make sure you put that in proper units. So that's 10 to the negative 9. So it's 10 nanocoulombs would be 10 times 10 to the negative 9 coulombs. Okay, the area, we're given the diameter of the disk, so make sure you plug in that correctly. To pi r squared, you'd have to plug in 0.01 meters for the radius. And again, we're given the gap, but at this point we don't need that information. And then this is a constant you're given. So hopefully you got that fine, and if you plug in numbers, the electric field here is quite large. Okay. 3,596,722 newtons per coulomb. Okay, now that's pretty big. That's a decent sized electric field, but that's actually of the same order of electric field that you need to create a spark. It's called the breakdown electric field of air. So it's not unreasonable, but again, intuition, we haven't built our intuition so far, but now we're starting to build it. So thousands, tens of thousands, hundreds of thousands, and even millions of newtons per coulomb is a reasonable electric field for depending on the situation. In this case, we have a pretty large amount of charge on these plates, okay, and very small plates. So large charge, small plates, which makes it a big electric field. Okay, so that's part A. Now part B, now that you have the electric field, can you do part B? So B is what kind of a problem? It's a kinematic problem, right? We have a proton, it's shot from the negative disk towards the positive disk, and so this is a kinematic problem. So I would encourage you to draw a picture of this and label the diagram with pluses, or with initial condition or initial variables, final variables, the direction of an acceleration, and a coordinate system, and all that. Go ahead and try and do that in solving this problem. Think the proton starts at a negative plate, goes towards the positive plate. Okay, and so think about all those directions. Try and get your diagram labeled first. Okay, so if you tried that, let me catch up to you. Okay, so if I've got a positive plate here and a negative plate here, okay, I'm given a gap between them. I'm going to label it as D. All right, and I've got an electric field pointing this way. And the electric field's pointing that way from the positive to the negative plate. And my proton starts here, and so I'm going to give it some values. I'm going to say that's T0, X0, V0X, and then it flies this way and ends here, because it says what's the launch speed must the proton have to just barely reach the positive disk. So this is our other point of interest. So looking here, I'm going to say that's T1, X1, and V1X. Okay, now let me get a coordinate system in there. I'm going to go ahead and choose the direction it's moving to be the positive direction. So where it starts I'll call 0, and I'll call to the left being positive X. Alright. Now with that, the last variable to get on there is the acceleration. So I'm shot from this plate and it barely reaches this plate. So is the particle speeding up or slowing down? So it should have been slowing down because it's moving and it's being repelled by the positive. So it's actually wanting to be attracted to the negative plate. So we shot it with a velocity this way. It's going to slow down and come back. The same thing as if I threw a ball up in the air. The ball wants to come down, but I initially gave it a speed upward. Okay, so that means my acceleration is this way. Okay, so that's my kinematic diagram there. Okay. Now the big connecting thing here is how is the acceleration connected to the electric field? Okay. Now that comes back to forces. We know the force must be that way. This would be my free body diagram, and I have only one force, and it is a Coulomb force. Okay, and I know that the Coulomb force is equal to the charge of the particle, so this would be the proton, times the electric field from whatever is acting on it. In this case, that's the capacitor, so I'll put CAP here. Okay, and the capacitor electric field points from positive to negative. Q is a proton, so it's positive, so the force is in the same direction as the electric field, which is true because we know the acceleration should be that way. So here's all kinematics. Here's a Newton's second law relating this to mass times acceleration. I better put an X here to emphasize it's the X direction. Okay. And so now I can relate the acceleration to the electric field. So now my acceleration is equal to Q E cap over M, and the direction is that way, which is negative. So I'm going to apply that direction with that minus sign right there. So I've got a negative Q E capacitor over M. I'm going to shift this over. It looks like it's a little bit fuzzy there. Okay. So now I've found that acceleration. And if I wanted to at this point, I could just plug in the number and get the value. I know the electric field, the charge of a proton is the same as the charge of an electron. Okay, so it's 1.6 times 10 to the negative 19. Again, it's on the front cover of your book. The mass of a proton is 1.67 times 10 to the negative 27 kilograms, also found on the front cover of your book. Okay, so I could calculate this right now, but I'm going to leave that to you. Okay, so I now have the acceleration. It's a number. I have used my knowledge of Coulomb's force in terms of electric field and Newton's second law to relate these two. Okay, so now we can just use this, and now I've reduced it to a kinematics problem. So I'm going to pause again, and hopefully you can solve it from here, but I'll be ready with some more advice to help once you're done. Okay, so now that you're back, we have an acceleration. We have some initial variables, some final variables. how do we find out the initial speed? So we're trying to find this one, and we know all the others. Okay, so I would make a list of knowns. I'm going to let you do that. I'm going to leave things in terms of variables and just solve for this v0x, because that's what I'm trying to find. I'm trying to find this initial speed. Okay, the big thing that's important that I do want to point out is this is 0. Why is that 0? Okay, the final speed is 0 because the problem says it barely reaches the positive disk. Barely is a code word for stopped. It didn't quite get there. It stopped. And so that is our big condition here. Okay, so using that as our important 0. Okay, there are some other zeros here, like x0 is 0. That's not an important 0. I mean, I'm going to use it, but it's not a conceptual 0. That's just I placed my coordinate system there. t0, I can say that's 0, but that's where I start my stopwatch. But this is an important 0. That's something that came from the physics of the problem. Okay, so I don't know much about time. I know my final velocity. I'm looking for my initial velocity. I know my initial position. I know my final position. It's a distance d. And I know my acceleration now. So which kinematic equation do you think would help me get that answer the most effectively? Okay, so the answer is that third equation. v1x squared equals v0x squared plus 2ax x1 minus x0. Okay. And recognizing that this is negative, it's got a minus sign. I'll plug that in here. This one is 0, that is 0, and I can solve for this one by plugging that in there, plugging the distance d in for that, taking the square root, and I'm good. Now I'll let you do that algebra, but just so you can check your answer. You get a v0x of 8.3 times 10 to the 5th meters per second. Okay. Now let's assess that. Now you may have gotten a number that's quite large, like to the 14th. I did that too, and I was like, whoa, that's way big. That's bigger than the speed of sound, or speed of light. It can't be that big. I realized I forgot to take my square root. Okay, so that's a good example of an assess. So this number is pretty fast, but it's quite small compared to the speed of light. And it's an electron. I mean a proton. A very small particle. The smaller the particle, the faster it can go. You can get protons even near the speed of light. So that's not an unreasonable speed for a proton. Okay, so let's go ahead and pause and let's start this next problem. So the next problem is problem 53. So go ahead and look at problem 53. Okay, so problem 53, what's the main idea? Okay, we have a negative plate, a positive plate, we have a gap, okay, and we have a particle that is launched with an initial speed at an initial angle. All right. And so the question is, what is the maximum initial speed the electron can have without hitting the negative plate? So if this gets shot too fast, it's going to fly up there and hit that plate. We want this to fly up there but not hit that plate. Now, why would it not hit that plate? Remember, it's an electron being shot, which means this wants to be attracted to the positive plate and repelled by the top plate. So there is a downward force. The electric field is going upward from positive to negative, and the electron feels a force downwards because F equals QE. It feels a force in the opposite direction. Okay. So, how different is this problem from this problem? Ask yourself that question. Can you use this problem to help you solve this problem? Okay, so hopefully you saw that you can. The only difference here is that we have two components. We have something moving to the particle has a component moving along the gap, and a component making it move across the gap. Okay. Now, it just so happens in this problem, you have enough to not even worry about the horizontal component. Since we're given this angle here, we know the component of the initial velocity upward, or at least we can write that in terms of the total velocity and this angle. And then this becomes not too different than this problem at all. Okay? So I'm going to let you explore this problem and apply it to this one, recognizing that you can break this into components and consider just the component across the plates with the one condition. There's one condition, like on this one, the V0 was, or this final speed was 0. Well, not wanting this to hit that plate, what's the maximum this speed could be and not hit that plate, means that the speed right at the top is 0, meaning that's its turning point. It's coming back down. Okay, so it's going to follow a line and come back down. So that means V1y should be 0. It's not moving up anymore. It's not coming down. It's at its turning point. So with that condition, you can say V1y equals 0. Then it really is just like this problem. So I'm going to let you solve that. And I'm going to write down the right answer here, which you can check your own answer. V0 is 1.19 times 10 to the 7 meters per second. Pretty fast, but also it's an electron. Electrons are even lighter than protons, so they can go pretty darn fast fairly easily. And that's the final answer. Okay, so you should work on that and make sure you can get that answer. Now, if there's any further questions, feel free to email me or stop by in our class if you have time. I hope again that you've taken a chance to pause every time I've paused, to pause the video and think about the next step. And hopefully these will get better as we continue to progress with them.